Example 2.4.5. Calculate the instantaneous power delivered by each phase of the system analyzed in example 2.4.3c at 3 different times, t equals 0 seconds, 2.1 milliseconds, and 4.2 milliseconds, and determine the instantaneous power of each phase to determine total power delivered to the three-phase load. Compare this answer with that found from P of t equals 3 times Vmax Imax over 2 times the cosine of theta. So it wasn't given in this problem statement, but in 2.4.3c we determined that the VA to N value was equal to 120 at an angle of 0 degrees volts, and that the phase voltage is equal to 2.4 at an angle of negative 36.87 degrees amps. So those were the phasor values of the quantity for voltages and currents in the Y-connected generator. We are asked to find P of t equal to 0, P of t equal to 2.1 e to the minus 3, and P of t equal to 4.2 e to the minus 3. And then we were asked to calculate and compare that to the power P of t equals V max Imax over 2 cosine of theta. So the first thing we need to do is, okay, well, what does this P of t mean? So remember that voltage written as a function of time is equal to V peak cosine of omega t minus theta V, and I of t is equal to I peak cosine of omega t minus phi sub I, and P of t is the product of instantaneous voltage and current, so we get that right there. So we need to throw in this omega t term right here. So we can do that just by taking the values for the phasors, plugging them in here, and then putting in these certain values for t. We do need to know what the value of omega is, and we know that it's for a three-phase system, so I guess it wasn't actually stated, but we're going to say that this is a 60 hertz system, so we're going to say that F is equal to 60 hertz, and that's going to be equal to 377 rads per second. Our phase shifts that we have here are in degrees, and so we need to convert the phase shifts over to radians, or we need to convert the angular frequency over into degrees per second. I happen to just know that 377 radians per second is equal to 21,600 degrees per second. And that just comes from the relationship that 2 pi radians equals 360 degrees. Easy way to always convert from radians to degrees right there. So we just need to plug that in for omega, 21,600. So if we want to calculate the values here, we get for phase A, because remember there's 3 phases, we get VAN of 0 times IAN of t equals 0, and so that's going to be, remember these are in RMS, so that's root 2 times 120 to put that into peak terms, times the cosine of 21,600 degrees per second times t, which is 0, and then plus the phase shift, which is plus 0 degrees. So that's the voltage. And then the current is going to be root 2 times 2.4 times the cosine of 21,600 times 0 minus 36.87 degrees. And that's going to give me a value of 460.8 watts there for the power on phase A. So now if we go to phase B, we need to calculate the power on phase B as VBN of 0 times I BN of 0. I'm writing N there. That's a little misleading, right? There's I phase A. It's a Y connected source, so there's only one current. Anyway, that's going to be root 2. Magnitude's the same, so root 2 times 120 times the cosine of 21,600 times 0. Now, the phase shift for B is going to be different. Remember that the voltage on phase B lags the voltage on phase A by 120 degrees. Now we need to do the same for the current. Current on phase B is going to lag the current on phase A by 120 degrees, so that's going to be minus 156.87. And so throw that into your trusty TI-89, you're going to get 264.85 watts. And then we need to repeat the calculation on the third phase. VCN of 0 times IC of 0. So it's just the voltage of the Y connected source times the current coming out of the Y connected source. So I think you get the picture here. It's root 2 times 120 times the cosine of 21,600 times 0 seconds. And then this is going to be plus 120 because it's the C phase. Then we've got root 2 times 2.4 times the cosine of 21,600 times 0, and then it's going to be negative 36.87 plus 120 degrees, so plus 83.13 degrees, and we get a value of negative 34.45. So at this time 0, each 3 of the phases is delivering a different amount of power. The total power at time 0 of the 3-phase system is going to be PA of time 0 plus PB of time 0 plus PC of time 0. So that's equal to 460.8 plus 264.85 minus 34.45. And that's going to give us an instantaneous power of 691.2 watts. So that's how we calculated it at time t equals 0. Next, what we wanted to do is calculate PA at t equals 2.1 e to the minus 3. And so that's going to be equal to root 2 times 120, which was 169.7, times the cosine of 21,600 times 2.1 e to the minus 3 plus 0 degrees. So that's the voltage. And then the current is going to be 3.394 times the cosine of 21,600 times 2.1 e to the minus 3, and that same phase shift as before, minus 36.87. And so on phase A at this time here, we get 400.29 watts. Need to repeat the calculation for the instantaneous power on phase B. I'm going to do a little shorthand right here. All these numbers are going to be the same, except right here it's going to be plus or minus 120 degrees. So I'm just going to use these tick marks to indicate that it's the same thing. Save ourselves some writing. And then it's just going to be 120 degrees out of phase of this. That's 156.87. Again, everything else is the same inside of these quotation marks. And we do that, and we get negative 55.94 watts. And then we repeat the calculation for P of C at T equals 2.1 milliseconds. And if we were to plug all those numbers in, the correct phase shift and everything, we'll get 492.32 watts. And then the total power is again just equal to 400.29 minus 55.94 plus 492.32. And that gives me a value of 691.5 watts. Almost exactly what I calculated at T equals 0. Off a little bit due to rounding errors. I'm not going to go through the whole calculation. You can do it for yourself, but the total power at T is equal to 4.1 milliseconds is going to give you a value of 691.2 watts. So again, the same number all three times. So that's the characteristic of three-phase power, is that because the voltage and the current between the phases are all 120 degrees out of phase, the power vectors are always going to add up to be a constant number. Basically their angles are always going to be adding up to 0 there. So we were asked to compare that with the calculation that was given in class, or the formula that was given in the textbook, that the instantaneous power is just 3 times Vmax Imax over 2 cosine of the angle between voltage and current, and so that's just going to be 3 that's going to be 3 times IRMS VRMS cosine phi. So that's 3 times, let's see, 120 volts times 2.4 amps times the cosine of 0 minus negative 36.87, so that's just 36.87 degrees, and we get an instantaneous power delivery of this circuit of 691.2 watts, considering all three phases. So I did that calculation just to show that the instantaneous power is the sum of the three phases, the power delivered on the A phase, the B phase, and the C phase. So that's total power. Total power is equal to the sum of the three instantaneous phases. And to demonstrate a second principle is that instantaneous power for the three phases is a constantly valued number. It never changes. Power per single phase changes as a function of time, but no matter when you measure, the sum of the three will always be a constant value. I did these calculations using a Y-connected source. I used VA is equal to 120 at angle 0 degrees volts, and IA is equal to 2.4 at an angle of negative 36.87 degrees. You could have done the same analysis for the circuit at the load. It's a delta connected load, and then we would have used VAB is equal to 208 at angle 30 degrees, and IAB is equal to 1.39 at negative 6.87. The point is that for the source we had to use the phase voltage and the phase current, and and for the load we have to use the phase voltage and the phase current, and they're different because of a delta in a load. We could run through the experiment or the example with either of those values though. We'd come up with the same numbers.